Good afternoon / morning, good evening, whatever time it is. Welcome to another Taco Tuesday. My name's Brett Zerba, and John's saying hello, so that's a good sign. He can already hear us. We're ahead of the game, which is unusual for us. If any of you that were signed up for our one couple of weeks ago and we had to postpone that, postpone it. We are going to reschedule it. I do want to apologize for our scheduling issue, but we chose to have about 50 international folks from Central America come visit us instead of spending some time online. We had them in person. So anyways, that's what we chose to do. So we apologize, but let's get going today. Again, my name's Brett Zerba. I'll be moderating today's event. Rich Medairos will have to we'll be doing the presenting on the train track, as you can see on his present. So if a couple of you can wave your hand, and so we know that you're hearing us. I think you are, because we're seeing some typing already. Any hand waving out there? Please, 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 couple. Uh-oh. Can you hear me, Rich? All good.
I can.
Michael says all good. Todd waved his hand. Okay, good. I know you guys getting used to Houston all that all the time, but anyways, no handouts today. Jazz hands. Kyle says jazz hands. A lot of highs and hellos and all good. Thanks, Frank, Kyle, Scott, Walter, David, Peter, and yeah, audio is on. Let's hope it stays on. It's a little wet up here in the Northeast today, but I don't think Mother Nature will affect us. So today's topic is something basic, but very important in our industry, right? Rich is gonna teach you how to do the fundamental way of piping system loss, pressure loss, drop calculations, right? And very important. And I can't emphasize enough how much Rich and I strongly believe, and we're old school. I'm a lot older than Rich, but we're both old school in our belief that you need to know the fundamental way to do things before you use all your software. And many of you have been on a computer since you were almost born. That wasn't the way all the time. So it's really important to know the basics behind it, in the theory and the thought process there. And then obviously to save time, you're going to use computer programs. We have one you can download. We'll probably be doing some more of that training in the next quarter on the HSS software. But nonetheless, I can't emphasize enough. It's so important to be able to do things like that. So no handouts today, but 24 hours, you'll get your PDH certificate email, as well as a recording of today's presentation. And by the way, if you do go to our website, tacocomfort.com, and click on the training tab, on the home page, one of the choices is training. Drop down and it says Taco Tuesdays. You click on that. At the bottom of that screen, you have access to the majority of the Taco Tuesdays that we've been offering, if you ever did want to catch up on one at some point as well. And Stanley just asked, is your pressure drop app free? It's actually a download. The answer is yes, it's free, but I would like to say it's a download that needs to reside on your computer, and it's more than an app, I would say. So look for it. Hopefully in October or maybe November, we'll have a class on that, and you can see the power of that and how easy it is to use to do your pressure loss calculations. So I think that's about it for, well, you know what, let me mention this. Some of you were on early and you may have seen a picture of the 5th generation, right? Two young little girls. So the company Taco is owned by the White family. Currently, Johnny White is the owner, and his 2 sons, John III and Benjamin, both work at the company, and they both are new fathers, over a year old now, but nonetheless, they both have daughters, Madison and Winona. So now, instead of 3rd generation, Grandpa Johnny, God, I don't know if we could call him that. I might get my hand slapped for that one. Grandpa Johnny, and then John III and Benjamin, and then you got Winona and Madison. So 5th generation, pretty proud for a manufacturing company, been around for almost 103 years now, pretty amazing, pretty amazing. And Thomas says, "Good morning from the West Coast." Well, you know, it's getting to mid morning. God, it's time for a coffee break. So it's still early morning, 9 o'clock. Anyways, I think I'm done yapping, Rich. So why don't you finish introducing yourself and take it away, my friend?
Sounds good, Brett. Thanks a lot. Appreciate that introduction. For those of you that haven't heard or met me before, my name's Rich Medairos. I'm one of the engineers here at TACO, and I am a mechanical engineer. I specialize in engineering and design of HVAC systems. And I am a PE registered in several states. And I've been doing this for, like Brett said, I've been doing it for a couple of years. I'm a little bit younger than Brett, so I've been doing it for, what have I been doing it now? 6 years, Brett?
Just about. Well, you've been at TACO 10, so we got to go up a little higher.
Oh, yeah, that's right. Yeah, been a takeoff. So we're going to talk a little bit about pressure loss, sometimes called pressure drop calculations. We're going to do the manual process here.
Hey, Rich.
Yes.
We got a question from Paul. Will you be on the screen soon? And the answer is, Rich and I firmly believe we have faces for radio. So the answer is no.
Yeah. If you see our faces, you might get scared. It's a little too early for Halloween, so.
There you go.
Yeah.
Take it away, my friend.
Okay, so let's talk a little bit about what we're going to do here. Let's see, does this thing work? I always love this when you press all the buttons. So let's talk a little bit about design criteria. What does that really mean? And we'll touch on water velocity and then water velocity pressure. Then we'll get into the pipe pressure loss calculations. And again, this is a manual calculation. And we're going to compare that against a computer calculation. We'll talk about fitting losses, valve losses, and we'll also define what the valve CV is all about. And as Brett mentioned earlier, you don't have to wait till the end of the presentation. You can type in your questions, and then Brett will ask me to stop periodically so we can answer your questions. So what do we mean by design criteria? Well, whenever we do a pressure drop calculation, we need to define some parameters. And most of the time, it's done as sort of an office standard. So in this particular case, we are going to set some very basic criteria. We're going to say that for our manual design that we're going to have a maximum velocity of 8 feet per second. And we're going to have a maximum pressure drop of 4 feet per 100 feet of pipe. So those are our criteria. And the other thing is that today's calculations will be based on clear water. Clear water is really a definition by the Hydronic Institute that we use here at TACO.
Hey, Rich,
and basically, it just means that water has a specific gravity of 1.0, and nothing's added to the water. There's no glycol. It's just basic water. It's not water that it's not considered potable water, but it's clear water. So, Brett, did you have a question? Or?
Well, a couple of people are saying that your volume is bouncing a little and it's a little low. So I'm not sure if I mean, I can hear you pretty good. So, but I'm not too concerned. But I did want to at least mention that.
Wow.
Yep.
Well, we'll do our best here.
Yep.
Okay, let's see what else we got here. And like I said a moment ago, specific gravity is going to be equal to 1.0. And we'll have today a maximum fluid temperature of 180 degrees Fahrenheit. So the very first thing we want to show is a very simple calculation. We want to calculate the velocity given the flow of 500 gallons per minute. And we have scheduled. Let's see if my pen works today, Brett. This would be kind of cool, huh?
My fingers are crossed.
Here we go. Whoa, look at that.
Oh,
so,
awesome.
We're going to be talking about a 6-inch Schedule 40 steel pipe and a flow of 500 gallons per minute. And we want to calculate the velocity. Well, before we actually calculate that, one of the things that I always like to point out when it comes to HVAC systems, and most of the pipe that we use is, well, a lot of the pipe is steel, Schedule 40 steel pipe. It's not always that because the plastic plays a big role today. And so doesn't copper. Perhaps copper less so because of the cost. So I think plastic and steel are probably the most popular pipe sizes for commercial projects. But anyway, the important thing to keep in mind is that regardless of the strength of the pipe, now we're talking about Schedule 40 steel pipe here. And if you'll notice in my little diagram, it says that the outside diameter is 6.625 inches and that the inside diameter for the Schedule 40 pipe is 6.065 inches. And the wall thickness is 0.280 inches. Now, the reason I like to point this out is because if we change the strength of the pipe, it's the inside diameter that gets smaller because the wall thickness gets larger. So the stronger the pipe, the thicker the wall, but the outside diameter remains the same. And the reason that is true is because if you're trying to connect different strength pipes in the same system, you need to have the outside diameters the same so that you could weld them together, or if you put on grooves in them, or whatever the case may be. And that's important to keep in mind because when we calculate the velocity, we're really interested in the inside diameter. And so we're going to do that. We're going to do a little quick calculation here. We're going to calculate the pipe internal area in square feet. And the way we're going to do that is simply use a very simple formula that says the area is equal to pi d squared divided by 4. And so if you want to convert square inches into square feet, we're also going to divide by 144. And in our case, our internal area is 0.2006 square feet. And we know that the velocity is equal to the flow in gallons per minute divided by the cross-sectional area. And then we have that constant in there. I'll define that in a minute. And so our velocity comes out to 5.55 feet per second. And that little asterisk is the calculation that we use for converting, making the conversion so that we wind up with feet per second. And so generally speaking, when we talk about hydronic systems, we always talk about the velocity in feet per second. So in our case here, it's 5.55 feet per second. All right, hopefully this will still work. Oh yeah. So here's a little table that I downloaded from the internet. These are readily available. And if you'll notice, we have for our example here, we have 6-inch pipe. And we said that we had a flow of 500 gallons per minute, which we have over here on the left-hand side. And it is, again, Schedule 40 steel pipe. And if you'll notice, under the column where it says velocity in feet per second, that's this little column right here, that they are publishing a value of 5.55. Whoops. How did that happen? 5.55. Oh, that doesn't look so good, Brett. We got to erase a little bit here. Here, let me erase this. It never erases when you want it to erase, right?
Yeah, I know.
Well, anyway, we'll go back one more time. Let's see if we can erase. Yeah, maybe that's a better way to do it. So I'll just point to it. So you can see that in this table, they came out with the 5.55 feet per second. And that's exactly the same number that we calculated. So it's good periodically to, if you're using a table or an app on your computer or an app on your phone, to do a simple calculation to make sure that the values that you're getting, and in this particular case, the first value that we're looking at is the velocity, and is the same that you can calculate. The value that you can calculate is the same that what's being published, and then you have some confidence that the published data is correct. Now, partly the reason I mention this is because I found mistakes in published data, and it can really mess with your design if you're using published data and it's inaccurate. So it's important to you don't have to do it on every single thing, but just periodically check to make sure that the information that you're using is correct. All right, so we just did this out, and so the next thing we want to calculate is known as the velocity pressure in head in feet. And the velocity pressure is equal to this equation here that says that the velocity in feet per second squared divided by 2 times the gravitational constant is going to be equal. In our case, we're going to use that same velocity of 5.55 feet per second. We're going to square that divided by 2 times the gravitational constant, which is 64.4. And the velocity pressure is 0.479 feet. And again, the asterisk is the gravitational constant of 32.2 feet per second squared. So if we go back to our table, we can see that under the column, again, this is 6-inch Schedule 40 pipe, and it's 500 gallons per minute. And you can see that the velocity head is 0.479. That's exactly what we just calculated. Let me just go back to make sure. Yeah, 0.479. Look at that. It's magic, Brett.
Wow.
So that's how we calculate that. Now, the friction loss in feet, this is the friction loss happens to be 1.66 feet per 100 feet. And that is done not by a straight calculation, but through experimentation over a period of time that manufacturers have published data about their piping. So those are the three values that we're most interested in today, is the velocity head, and the pressure drop in feet per 100 feet. Okay, let's continue along here. Now, when we do an actual pressure drop calculation, we're going to use the equivalent length method. And what we're going to say is that, well, let me go back one more time here. I'm going to erase these little dots so it doesn't become too confusing. But I just said that the pressure drop in this pipe here at 500 gallons per minute, a 6-inch pipe, again, I'm circling some stuff here so we're all on the same page, that the pressure drop in feet per 100 feet, in this case, is 1.66. So if I had a piece of pipe, this particular pipe is 6-inch diameter, and I was circulating at 500 gallons per minute through this pipe, I would see a pressure drop over that 100-foot length of 1.66 feet. That's what that means, 1.66 feet. So when we talk about using the equivalent length method, we're saying that, well, how much pressure drop is there in a fitting in equivalent length? So more specifically, let's say we have, let's use this example here. We're going to point to this 6-inch diameter pipe. And for a standard elbow, it has an equivalent length of approximately 16 feet. Can you see that okay, Brett? I know the lettering is a little small.
I can see it.
So in other words, if I had a standard elbow, my handy dandy little sketch here, it would have the same pressure drop through that elbow as if it was going through a 16-foot section of pipe, 16 feet. If I had a section of pipe that was 16 feet long, the pressure drop across this little elbow would be equivalent to the pressure drop across 16 feet. And let me put 16 feet there. Okay. So let's look at a couple of other examples here. So there's the first one is a standard elbow, so check that off. The second one is a medium radius elbow. Look what happens to a long radius elbow. And again, we're going to go back to our 6-inch diameter pipe. The long radius elbow has an equivalent length of 11 feet. So you can see that if I chose to design my system and I used standard elbows in lieu of long radius elbows, I'd have a slightly higher pressure drop. So one of the ways in which we control pressure drop in the system is by selecting fittings that had less pressure drop or a shorter equivalent length. Okay. Let's just skip down here, for example, to a globe valve. Now, I wouldn't expect you to use a globe valve in an HVAC system designed for normal flow in a piping system. You might use a globe valve for the shutoff of a hose bib or something on that idea. But look at the length, the equivalent length of pipe. It's 160 feet long. That means the pressure drop across the globe valve would be equal to a straight length of pipe of 160 feet. If we look at a gate valve, you'll notice over here the gate valve is only 3.5 feet. The pressure drop across a gate valve is less than the pressure drop across a standard elbow. So when you decide the components that you want to use in your system, you have to keep in mind what the equivalent length is of the different components. A full port ball valve, for example, has a very, very low pressure drop, even less than a gate valve, probably around, say, 1 foot per 100 feet or something in that order of magnitude. So hopefully you get the general idea that when we talk about fittings, we're talking about equivalent length of straight pipe. Any questions about that, Brett, before we go
Not specifically, but we have a couple questions / comments.
on? Okay.
Can you give us an idea of how you downloaded that piping system pressure loss table? You know, the first table you kind of showed.
Yeah, I just went online and I typed in under a Google search rather. I just typed in pipe pressure loss for inch pounds, and I was able to find this. Usually, the piping manufacturers will provide you with these different tables
as well.
And so they're readily available online if you want to get a printed table like this in a PDF. But there are a lot of apps out there that you can download and put on your phone or on your computer that does the same thing. And our HSS software also has that information embedded in the software.
And then can you go back a couple of screens where you showed, I think it was your first calculation. Dude, let's see, where you had the area of the circle. Area. Yep. Somebody, Bo, pointed out the area of a circle is pi times radius squared. Maybe not, is that what your internal area? You have pi times diameter squared. So,
well, remember the equation is for the area is equal to pi r squared, or if you want to use the diameter, the area is equal to pi d squared over 4. And
all right.
That's what this, you see the 4 value right there?
Yep, there it is.
So that's pi d squared over 4. And then because we want it in, the units are in square inches, we want it in square feet, it's 144 square inches per square foot.
We got some people on the ball today. Stanley says but he divided by 4. So we got the mathematicians out there. Our good friend Drew Wolf is asking a general question here, and you may want to discuss it a little more during the CV. But when does CV come into play versus pressure drop for a valve?
Oh yeah, we have that a little bit later. So let's hold off on answering that until we get to that part of the discussion.
Fair enough.
All right, so we've already gone through this. And we talked about equivalent length. Okay, so hey, look, that's where we are next.
Perfect.
Perfect. So CV stands for valve coefficient, and by definition, the CV of a valve is equal to the flow in gallons per minute at a 1 pound per square inch pressure drop when the valve is 100% open. So for example, if I had, let's say I'm looking down from the top, and I have a piece of pipe. Here's a piece of pipe. Does that look like pipe, Brett?
It does.
It does.
Pipe, but pipe.
Okay. If I'm looking down from the top, and let's say I happen to have in this section a pipe right here, let's say I have a butterfly valve, and the butterfly valve is partially open, so it might be at an angle like that. And I can take that, I can look at that same set of pipe again, kind of making a quick sketch here. There's another section of pipe. This time, the valve is 100% open because it's parallel to the flow of the water. And so that would be sometimes we call it the wafer or the disc as part of a butterfly valve. So what is the CV of let's assume it's a butterfly valve. And the pressure drop across the valve, let's say again in our case, I'm going to make this up. Let's say it's 500 gallons per minute. We're using that initially, 500 gallons per minute. 500 gallons per minute. If the valve had a CV, let's just put it in here. Let's say the valve had a CV equal to 500, then that means that it would have a 1 pound, 1 PSI pressure drop at 500 gallons per minute. So that's what that definition means. So let's look at a couple of examples of CV. Let's see here. So here's an example. A valve with a CV of 25 will have a pressure drop of 1 pound per square inch at a flow of 25 gallons per minute. So it's pretty simple. It can get a little bit confusing when you start looking at CV tables, but hopefully we can clear that up in a second. Oh, and the other thing, in terms of units, US units, we call it a CV, and the metric system, they call it a KV. And so again, if we had a valve, again, of a CV equal to 25, that means that it will pass 25, it'll allow rather, 25 gallons per minute. I'm just repeating what's on the left side here, at a 1 pound pressure drop, at 1 PSI pressure drop. If it's a KV, it would be metric and it would be cubic meters per hour at 1 bar, and that's the definition. And we can also, I have a little paragraph over here. I'm not going to read the whole thing, but basically these are the conversions. If you have, if you are looking for the CV and you're been given the metric value, if you multiply by 1.17, you can convert that into a CV value. If it happens to be a CV value and you want it to be in a KV metric system, you would take the CV value multiplied by 0.86. So that's a couple of conversions that might be of value to you. Okay, before I go on, Brett, any other questions hanging out there?
So I guess back to Drew's question comment, some valves you'll see CV information, and other valves they'll actually give you the pressure drop, I guess.
Yeah, and most of the time, when it comes to sort of generic valves like ball valves and things like that, they generally don't publish the CV value, or they'll just give you the pressure drop. Most of the time, manufacturers publish the CV value as for control valves,
right,
or zone valves, or things like that.
Something electronic, more, yeah.
Yeah, generally speaking, something that has some kind of control function. In fact, here we have a little table.
Another segue.
Another segue. And this is the zone sentry valve manufactured by Taco. And this little table tells us what the CV value is. So we're going to take, for example, take 3/4 inch diameter pipe. I'm sorry, a 3/4 inch diameter valve. And the first value here, well, let me go up the top here. The first value is CV, the one in parentheses is KV, and the last one is the feet of equivalent length, all right? So in this case, it's 10.3. What that means is that this valve will allow 10.3 gallons per minute to pass through the valve at a pressure drop of 1 PSI, all right? And if you remember from that previous slide, if I multiply the CV by 0.8, what was it, 0.87? Let's go back here. So I don't.
6, no? 8.6.
0.86, yeah. So if I multiply that 10.3 times 0.86, comes out to approximately, let's see, I did that. No, that's right. It comes to approximately 8.9. And there's that KV value that we put in parentheses. See that?
Yep.
And it has the equivalent length of 8.4 feet. Isn't that cool?
Wow.
Now that's a two-way valve. And if you notice over here on the right-hand side for our three-way valves, we have the same set of values. The first one's a CV, the second one is KV, and the third one is equivalent length of feet. Very cool stuff.
And then you need to convert the 1 PSI into feet.
Yeah, but most of the manufacturers will give you that information, so you don't have to worry about it.
Yep.
But if it's feet, it would be equal to 2.31 feet. 1 PSI is equivalent to 2.31 feet. Pretty cool.
Yep. So we have a question about CV.
Let's have a question.
Does the CV have any importance in pressure independent valves?
Well, pressure independent, depending on the type of valve, the most common is called a PIC valve, pressure independent control valve. And generally speaking, the CV that's associated with a pressure independent control valve or a PIC valve is generally at the design or the characteristics when the valve is 100% open. And so a PIC valve is kind of an odd thing because the actual characteristics of the valve change as the inlet pressure increases or decreases. But if you had the maximum pressure yes, if you had the maximum opening of the valve, the CV would relate to the valve as if it was 100% open.
Yep, makes sense.
Okay, any other questions?
Nope, move on.
Moving on. All right, so we have a very, very simple little diagram, and we're going to now do a manual calculation for the pressure drop. And we're going to use what is known as the point-to-point method. So I have a slide I'm going to show you in a second, but let me try this. I'm going to try putting black on here. And let's say at the discharge of this little boiler here, that's point number 1. Put a little number 1 there. Does that look like a 1? I guess it does.
Yep.
And then the inlet to the pump is point number 2. The outlet of the pump is point number 3. Now follow the valve, I'm sorry, the pipe all the way down. The inlet to the fan coil is point number 4. Now, if I keep numbering them manually, then let's see if this comes up. Let's see if I did this correctly. There's 5. The inlet of this is 6, and then 7, and then 8, and then 9. Then way back here, this should be point 10. Now, if I did that correctly, on my next slide, I should have the numbers correctly. So in our case, we have the maximum velocity. We want to remind everybody of our initial design criteria of 8 feet per second or less. We want to have maximum pressure drop of 4 feet per 100 feet or less. So in our case, we have to decide first what the pipe is. So let's go back here. Let me erase these numbers. Well, I'll leave them on there for a moment.
As Rich is moving from screen to screen, I do want to re-emphasize that this is for HVAC hydronic calculations. This is not for domestic or anything like that, right, Rich? That's a different ballgame.
You could use the same methodology for domestic water, but you typically have different design criteria. Instead of allowing 8 feet per second, domestic water is usually much less of allowable velocity. And the pressure drop per 100 feet for domestic water might be different. So the design criteria for the HVAC system that we chose is pretty common. The methodology for doing the pressure drop calculation for domestic water is the same, but you usually have different criteria that you're trying to stay within. But for today's discussion, it's only HVAC.
Yep.
Okay, if you'll notice, our little system here has 61.5 gallons per minute. And I'm going to come back to the slide in a second. So my first thought would, well, can I do that with 2-inch pipe? Well, you can see I don't have a value here for, whoops, I don't have a value. Let me try erasing that. One more time. Try erasing it one more time, Rich. Okay. So I don't have a value for 61.5, but I do have one that's fairly close. I've got 60 gallons per minute. And that 60 gallons per minute with a 2-inch pipe up here, Schedule 40 pipe, that would have a velocity of 5.74 feet per second. And that's less than 8 feet per second, so that would work. But let's go over here to the pressure loss. Look at the pressure drop. It's 6.59 feet per 100 feet. But we said we wanted to have a maximum of 4 feet per 100 feet. So that 2-inch pipe is too small because it doesn't, excuse me, it doesn't qualify for both of the categories. So let's go to the next size pipe, 2.5-inch. And again, we're roughly around 60 gallons per minute. Excuse me 1 second, Brett. I have to clear my voice here. Take a drink of water. Okay, I'm back. Sorry about that.
No problem.
So at 2.5-inch, look at the velocity. Well, it's less than 8 feet per second, which you would expect. Ooh, what happened here? Let's go back. Yep. It's still writing. So if you'll notice, it's 4.02 feet per second. So it meets the criteria of less than 8 feet per second. And the pressure drop is now 2.72 feet per 100 feet. So that means that it meets the criteria of 4 feet per 100 feet. So we've met both criteria. We've met the velocity, we're less than 8 feet per second, and we're less than 4 feet per 100 feet for the pressure drop. So the 2.5-inch pipe is the correct size. So let's continue on. I've made my selection. It's 2.5-inch pipe. And now I want to number those points from point to point again. Let's see if I did this correctly in this diagram here. Look at that, it worked. And I got the same numbers that I wrote down manually.
Pretty good.
So I want to now create a little table, and I want to do the point-to-point calculation. I want to do the pressure drop from point to point. So for example, I have a piece of pipe that's connected to the discharge side of the boiler. That's point number 1. And then to the inlet of the pump, and I have a section of pipe. So let's say we put that in a table format here. How are we doing for time, by the way? Oh, we're doing great. Okay, so from point 1 to point 2, there's my point 1 to point 2, and that's item number 1 in my little chart. I've got 2.5-inch Schedule 40 steel pipe, and the pressure drop for that pipe, or the length rather, is 2 feet. I figured out the length on that. Perhaps I had a scale drawing and I measured it. Or in AutoCAD, you can, if you're doing your drawings to scale, you can just click from point to point and you can find out the exact length. So let's assume in this case it's 2 feet. And then from point 3 to point 4, it's 20 feet, and so on and so forth for each section of pipe. I have these different lengths. And if you'll notice, I simply added those lengths up, and I came up with 130 feet of pipe. Okay. Oh, I'm sorry. I apologize. Whoops, I got ahead of myself, Brett.
Yeah,
I really
jumped
did.
up a little.
I jumped up a little. Let me erase that. Okay, so I also have some 90-degree elbows. And if I go back, let's go back to my drawing and just let's just add up the elbows I have. So here's 1. I'm going to circle them so you can see. There's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've got 12, approximately 12 elbows, right? Give or take. Whoops. Why does this keep going back?
A lot of jumping today.
A lot of jumping. Very jumpy. So what did I just say? I had 12?
12.
12. Okay. If I multiply that times 1.5, which is a reasonable factor, that's 18. So I'm going to round it off and say I've got 20. I got 20 elbows. So you see the methodology. I counted 12. I multiplied 1.5 times that because I wanted to have some additional values in there for fittings. And then I rounded it off to 18. And that's what I put in my table over here. So let's go back. So I put in 20 on my table. And for a 2.5-inch Schedule 40 pipe running at roughly 60 gallons per minute, it's equal to 6.5 feet. So 6.5 times 20 is 130 feet. So 130 is equivalent to the elbows, which are the fittings in this little simplified example. Then I have to add the length of pipe. So I've got, you can follow along the arithmetic with me. 2 plus 20, that's 22, 24, that's 44, 46, 46, and 130 is 176. Did I do my arithmetic correctly?
I think you did.
I did. And then the pressure drop is 2.72 feet per 100 feet. And so if I multiply 176 times 2.72 divided by 100, that's approximately equal to 5. Let me do my arithmetic out here just to see how close I get. 176 times 2.72 divided by 100, that comes out to 4.8, and I rounded it off to 5.
We'll let you get away
Any
with it.
questions about how I came up with pipe and fittings? That was my first little chart here, pipe and fittings.
We actually have two folks of asking, well, what's the penalty of oversizing pipe, or consequences?
What's the penalty for overestimating the pressure drop? I think that's really what they meant to say.
No. Picking a diameter of 3-inch instead of 2.5, or 4-inch instead of.
So if you make the diameter too large, then your velocity gets quite low. So most of the time, in terms of HVAC systems, most people want to be in the range of between 6 to roughly 10 feet per second. Oops, FPS, feet per second. If you get much higher than 10 feet per second, you run the risk of wearing the pipe out prematurely. When the water flows through the pipe and hits an elbow, it slams into that elbow, and over time it'll cause that elbow to erode and eventually fail or leak. If it's much lower than 6 feet per second, then the air that gets entrained in the pipe, the air bubbles will actually attach themselves to the inside wall of the pipe, and they'll stay there, and they'll help corrode the pipe. So you want to have high enough velocity to move the air along, but you don't want to have too high a velocity so that you slam into things like fittings and wear the pipe out prematurely, which is why most engineers will probably have a range. Now, in our case, we said less than 8 feet per second. So the larger you make the pipe, the lower the velocity, and the more risk you have of collecting air and not moving the air along and removing it from the system. Does that help in that explanation?
Yep. And Chris asked, please explain the importance of minimum velocity. I think you just covered that. Air is probably the biggest
Yeah,
issue.
we want air to move along with the water stream and then be taken out by the air and dirt separator. In order to increase the life expectancy of the pipe.
So obviously cost comes into play, right? If you can get away with a 2.5 and you put in a 4, well, I think we can all agree it's going to cost a little more. But it also lowers how much head you're going to put on the pump. So sometimes that comes into play. There's all pluses and minuses, and maybe if you're a design build, or if maybe you have a lot of 4-inch pipe and you want to get rid of it, or a 3-inch pipe or something like that. So there's different ways to look at it, but here's the details right in front of you, right? And those charts can spell it out for you for the most
Now, keep in mind that all the stuff I'm doing is very simple, very straightforward. There's no magic behind the scenes. We can reproduce these numbers, when we go back and forth between our tables and our diagrams.
Yep.
So the first category, again, was pipe and fittings. Now let's go to the next category and talk about equipment and control valves. So here's the one that always catches everybody. So if you'll notice, remember from point 4 to point 5, I had a fan coil in there, and the pressure drop for the fan coil is 10 feet. Now here's the mystery question, Brett. Is anybody out in the audience can tell me how I calculated that pressure drop? Does anybody want to type in and?
We'll see. We'll see if anyone. Oh, Mr. Wolf said manufacturer.
That's correct.
Akash says equipment manufacturer.
Drop in someone's pieces of equipment. Only the manufacturer can tell you what the pressure drop is, because we don't have access to what their piece of equipment is designed for. So in this particular case, I had to go to the manufacturer's data, and for this particular fan coil that I selected with a flow of around 61.5 gallons per minute, its pressure drop was 10 feet. And that's published data. I can't calculate it. I have to go to the manufacturer and look up that data. Also true of the control valve. We have a control valve in there, and the control valve has a CV of 50. Now, here's something we will provide some calculations for. If the control valve has a CV of 50, that means that that valve will have a 1 PSI pressure drop at 50 gallons per minute. Is everyone in agreement with that, Brett?
Yep.
So now our actual flow is greater than 50 gallons per minute. It's actually 61.5, if I recall. So we have to use this equation. We have to say that the final pressure, now let's say final pressure is equal to the initial pressure, I'm going to put PI here, times the ratio of the flow. In this case, we need 61.5 divided by 50 squared. Look at that.
Yep.
So if I take that 61.5 divided by 50, that's approximately 1.23, and I square that, well, that comes out to approximately 1.5 times the initial pressure of 1 PSI. My new pressure drop is equal to 1.5, and I've multiplied that by 2.31 to convert it into feet. That comes out to approximately 3.5 feet. And look at that, magically, it's right there at 3.5 feet. So that's how I can convert my pressure drop given the specific information on a control valve. If I'm flowing more than what the CV value is, I can use this little equation down here and calculate the pressure drop. And in my little example here, I carried it over, I rounded it off to 4 feet. So the actual calculation was 3.5, but I rounded it off to 4.
I want to give a shout out to Stanley. He mentioned that in the question things. The benefit of CV is to allow user to calculate the valve pressure drop at flows other than the CV flow.
Yeah.
Which is what you just did.
Well,
So
yeah, that's great stuff.
Shout out to Stanley.
Now here is the air separator. You get that from the manufacturer. The boiler, you get that from the manufacturer. And you add up all those numbers. Let me just erase the red lines here so it gets a little confusing. So 10 and 4 is 14, 5 is 19, and let's see, that's 30. Yeah, if I add all those numbers, they come up to 30. The grand total is 34.7, or roughly 35, because if you notice, remember from the valves and fittings,
Pipe and fittings.
not pipe and fittings, I'm sorry, pipe and fittings, it was around 5, it actually was 4.7. So the pressure drop for our little system here is 34.7 feet. Again, the pressure drop is in feet up here. So let's see what the computer calculated. We did this manually, and we did this using the HSS software. And if we take that little green tab away, drum roll please, Brett. 34.7 feet is calculated pressure drop, total pressure drop, with a 50% safety factor, 1.15. The total pressure drop is approximately 40 feet and we're going to select the pump in a minute at 65 gallons per minute at 40 feet. But before we get into that selection, there's that value of 34.7 feet before we add the safety factor in there. So the pressure drop that we calculated manually was exactly the same pressure drop that the HS2 software had calculated. And then we added a safety factor of 1.15 to add 15% to that, and that came out to approximately 40, not exactly, but we rounded it off. So let's do our math. 34.7 times 1.15, that number actually came out to 39.9, and I rounded it off to 40. And when I make a pump selection, I generally don't make the selection for the exact flow in gallons per minute. I usually add a little safety factor there. In this case, I added a safety factor and rounded it up to 65 feet. So if I'm making a pump selection, in order to accommodate this little system, it would be 65 gallons per minute at 40 feet. So I've done the calculation both manually and also used the software. And if you'll notice, I came up with exactly the same value because I'm using the same input data. I mean, the same data that the software is using is the same data that I used. So I have to come up with the same number. Any questions about that, Brett?
Not about this. Are you at a point where you want to handle some outstanding questions?
Yeah.
All right.
Okay. Hold on. Let's see what. Oh yeah, this is where we ask questions.
So on the CV chart for three-way valves, maybe you might want to go back to that.
Want to go back to that? Yep. Let's go back a few slides here. There it is. Let me shut off the all the little lines here.
Yeah.
Okay, go ahead.
It's actually for the three-way valves. I think it was
these guys out here. Right?
Is for straight flow through straight or branch flow?
That's considered to be the branch flow.
Okay. And then another question: if the flow is 10.3, right? We show that for the 3/4 inch one. 1 psi. Why is it not 1 times 2.31? How do we get to 8.4 equivalent feet?
Oh, because the 8.4 is equivalent length of pipe.
Right.
It has. It's not equivalent feet of pressure drop.
And then if you go to your diagram, I hate to even mention this one, your sketch that you did the point-to-point, not your sketch, but the HS2.
This little guy here?
Yeah, so I know what your answer is going to be, but I think it's prudent that we say this. Why is the air separator and expansion tank not at the lowest point of pressure and highest temperature?
Well, again, this is an oversimplified diagram for purposes of training and pressure drop. So don't do this. Don't build this.
Don't build.
Don't build this.
Don't build this.
Yeah, this is really for instructional purposes. You'd have a little bit more thought in terms of where you would locate the expansion tank and the air separator and all that other kind of stuff. We're just doing a pressure drop calculation.
Yep. Bryce just wanted to point out lower velocity can also lead to miscellaneous and train impurities settling out in the pipe, which is
that's a good point. Yes,
a very good point as well.
Yeah.
And Michael is making a statement, and you and I need to probably get a little more up to speed on this. For energy conservation, ASHRAE provides recommended standards for maximum pipe velocities and flow rates based on pipe sizes, hours of operation per year, constant versus variable speed, noise sensitivity, blah, 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 blah. So 4 feet per 100 and 6 to 10 feet per minute are only a starting point. Need to see the ASHRAE charts. So I think that's something that you and I should also mention or agree with, I'm sure.
Yeah,
right?
yeah. I mean, for today's discussion, I oversimplified the problem. If we went through ASHRAE, we could manipulate the design so that it would comply with our what do we say, 8 feet per second and 4 feet per 100 feet. But yeah, ASHRAE gives us much more in the way of guidelines in terms of what we should select.
And here's a great one. We've done this presentation. You've done this presentation a few times. This is the first time someone's asked this. How does an open piping, like a condenser water calculation, does that change or does it remain the same? So if you're doing a cooling tower and it's open, how does the pressure drop calculation change, if at all?
Well, that's a great question. So let me see if I can. You know what? I'm going to try this, Brett. There's always an issue here. If I go to, I'm going to try going to my whiteboard here. Will it work? Sometimes it works, and it all depends on the day of the week. It is.
Configuring.
It's thinking. The whiteboard is thinking, and so we're going to try loading a clean whiteboard. Oh, there we go.
I think it did.
Hey, it worked. So if it's an open system, for example, we actually had this a couple of weeks ago.
Yep.
But let me do the most common one, and that's the cooling tower. The cooling tower, let's assume we have a cooling tower, and the cooling tower, this is in the upper left-hand corner here, and it has a basin, and that basin is where the water is kept. There's a fan at the top in my little oversimplified cooling tower. And then there are a couple of containers or basins at the top, and sometimes these are called the hot deck, and sometimes down here it's called the cold deck. Okay, so if I have, I'm going to try, let's see, can I move this? I can, oh, I can. Yeah, oh, look at that, Brett.
There you go.
There I go. Let's get rid of this junk over here. We don't care about that. All right, so we've got a hot deck and a cold deck, and so if I have there's a piece of pipe and it's connected. Ultimately, it's got some elbows in it, and eventually it goes to a pump. This is the little symbol that we use for pump, and maybe that goes into the condenser side of a chiller. I have it come out the other end, so I'm just going to call this CHILLER. How's that? Chiller. And then it goes, all kinds of different fittings and valves and maybe strainers and a whole bunch of other stuff. But ultimately, it comes back here, and I'm going to really make it goofy looking, and feeds the hot deck. And it's usually on both sides of the cooling tower. Now the pressure drop calculation is done exactly the same way that we did it before. We have the pipe, we have the fittings, we have the equipment, and maybe we have a control valve over here, or maybe an isolation valve. So I'll stick an isolation valve over here somewhere. And maybe there's a CV associated with that. So we got pipe, fittings, equipment, control valves, all of that stuff. And you do the pressure drop calculation, and in addition to that, so that's going to be the friction. So we have the calculation for the friction. And I'm just going to arbitrarily make up a number here. And let's say the pressure drop from my friction calculation comes out to, I'll make up a number, say it's 60 feet. There's a number for you. In order for the pump to overcome the height of the cooling tower, I have to take the water level that's in the hot deck and the water level that's in the cold deck, and those two elevations, let's assume that that vertical distance is 15 feet. I have to add that, which is sometimes referred to as my static head. I have to add that static head, in my case 15 feet, so 60 plus 15 is 75 feet. So whenever I have an open system, I have to do not only the pressure drop calculation as a function of the pipe, but also I have to consider the static head or the height that I have to raise the water to accommodate this tank configuration here.
Just to reiterate, the pressure loss calculation and the numbers associated with the values and everything you showed earlier in the point-to-point method are all the same, right? I mean,
that's correct.
Yeah, there's no difference per 100 and all of that, and for whatever all your values were, your limiting values for velocity and maximum unit head loss, whatever, all that remains the same, and then you just have that additional static that you got to take into it. Right?
Yeah. So so we actually had this problem a couple of weeks ago. This was interesting. This was a real problem that somebody had. And what they did was they had a tank that had water in it. And they had another tank up here that had water in it. And they put a valve here. I'm sorry, they put a pump right here. And they drew from this tank into the pump. And then from this, they pumped all the way up till they got to, oops, I went a little bit too high there, to this tank here. So we had to calculate the water level difference for the static head. So that was the distance from here to here. And we had to calculate the pressure drop, which is, again, the pipe. And that's not the best elbow in the world. Let's assume there's an elbow there, there's pipe there. And there was a control valve over here. And we had to do all of that calculation plus the water level. And in our case, I think it was like 30 feet, something like that, for the height of the different tanks. So yeah, that's how it's done.
And to clarify or to reiterate, in a HVAC hydronic closed loop system, the height doesn't really come into play per se, correct?
Not in terms of the pressure differential required by the pump. The height then becomes more of an issue in terms of what's the total pressure in the system if your pump happens to be at the bottom of the system at the lowest elevation, or your equipment's at the lowest elevation. What is the pressure as a function of the static height plus the pressure differential of the pump? And that has more to do with the design operating pressure than it does to do with the pressure drop calculation. But to your point, if it's a closed loop pressurized system, we do not take into consideration the height of the fluid for the pressure drop calculation, only in open systems.
And so Heidi asked, what about static head of cooling tower above pump level? So that's not added in at all then, right?
Say what's the question?
What about static head of cooling tower above pump level? I don't really.
No,
I guess,
no, it's only the difference in the cooling tower height, because even though we think of a cooling tower, it's actually two tanks. One is up here. This is a cooling tower. This is an oversimplified cooling tower. And the other one is down here. So if we're pumping from the lower tank to the upper tank, there's a pump. That's not the best pump in the world. To the upper tank, then we take the water level difference between these two for our static.
Yep.
And, you know, if it's a small cooling tower, that might be in the range of around 10 feet, maybe for a larger cooling tower, it might be 15 feet. Now, when it comes to gigantic built-in-place cooling towers, that could be 40, 50, 100 feet.
Right. We're at the end.
We're at the end.
Well, I mean, it's 1 o'clock, and we're out of questions. So finish up.
All righty. So at this point, let's see if we can go back to our presentation without screwing this up here.
Uh-oh.
Oh, can we do that? Look at that, Brett.
Wow, man, oh man.
Man, I tell you, sometimes it works.
It's not our first rodeo.
So at this moment, I want to thank everyone for participating in today's little discussion and manual pressure drop calculations. Hopefully you got something out of it. And with that, I'm going to turn it back over to Brett. Brett, take it away.
Yeah, Rich, great job as usual. Fantastic. A lot of thank yous and pats on the back. Great session. Thank you, thank you, thank you. So as usual, great job. And everybody, thanks for your time. We appreciate it. Look for the next quarter schedule for Take-O Tuesdays. It'll be out shortly. Other than that, we are signing off, and somehow I can say goodbye. Goodbye, everybody. Look for your emails tomorrow. Take care.